quantum field theory is the modern interpretation of quantum mechanics. It is our understanding of the subatomic world. And we realized through our investigation of the subatomic world that the vacuum is alive, that when you zoom down into the tiniest, smallest scales in the universe, particles, fields, energies are constantly popping in and out of existence, floating in and out of existence, being created and being destroyed in a flash of an eye. And this turmoil has an energy associated with it, that the vacuum of space time itself has an energy.
What's up, everybody? From Nautilus, I'm Brian Gallagher, and you're watching Behind the Scenes. Today I'm speaking with Paul Sutter. Paul is a theoretical cosmologist, award-winning science communicator, essayist, podcast, speaker, and TV host. He holds a professorship at the Institute for Advanced Computational Science at New York University and a guest researcher position at the Flatiron Institute in New York City. He is also the author of Your Place in the Universe, Understanding Our Big, Messy Existence. And his recent story in Nautilus was The Remarkable Emptiness of Existence. Paul, thanks for joining us.
Oh, thank you so much for having me. I love talking about nothing.
It's a stimulating subject. To start off, would you mind summarizing your intellectual and academic background?
Yeah, sure. I got my PhD at the University of Illinois at Urbana-Champaign in 2011. While I was there, I was a Department of Energy Computational Science graduate fellow. So I was funded by the Department of Energy specifically to focus on computational science, which is using big giant computers to solve our major outstanding problems. The major outstanding problem I was interested in is the nature of dark energy and dark matter and the ultimate fate of the universe. From there, I went to the Paris Institute of Astrophysics, where I spent 3 years as a postdoctoral researcher. And then from there, I spent 2 years at the Trieste Observatory in Italy, another postdoc position there. I came back to the States, worked a position at the Center of Science Industry as a chief scientist there in Columbus, Ohio, along with an academic position at The Ohio State University. And for the past I want to say 5 years now, I've been based in the New York City area, doing tons of science outreach and really generally having a good time.
Excellent. You want to give us a brief sense of how you came to be interested in these questions of cosmology and astrophysics? And perhaps you could say what drew you to science in the first place.
Yeah, these are one of those topics where I've always been interested in science in general since I was a kid. I remember reading book after book after book when I was a kid, just gobbling down anything. But I never actually realized that science was for me, that I was capable enough, that I was intelligent enough to do science. And so when I went into high school and went to go pick a college, I actually majored in computer science, in computer programming, because I was still a giant nerd, don't get me wrong. But it never clicked that being a professional researcher scientist could be a thing for me. 3 years in, I took an astronomy elective, fell in love with it all over again. The professor took me aside and said, "Look, if you want, you can become a physics major. You can just do this." And less than a week later, I switched majors and I never looked back.
That's pretty cool. Would you like to give us a brief summary of your story for our viewers who haven't read it yet?
Yes, in this story, I investigate the nature of the nothing. And I go back and I start the piece with the exploration of the nature of the vacuum in medieval and Renaissance Europe. And there's this fascinating character named Otto von Guericke. He was supposed to be a mayor of this random German town. But instead, he was always busy playing around with these experiments. And he invented an efficient vacuum pump that could suck the air out of two sealed hemispheres. And to demonstrate that he was actually producing a vacuum, that there was nothing in those hemispheres once he pulled all the air out, he set up this elaborate demonstration where teams of horses were attached to either end of the spheres, and the horses couldn't pull it apart because of all the atmospheric pressure pressing in on those spheres. After that, scientists came to accept the idea of the vacuum, the idea of the nothing. But then in the 20th century, this idea got turned around with the discovery of something we call quantum field theory. Quantum field theory is the modern interpretation of quantum mechanics. It is our understanding of the subatomic world. And we realized through our investigation of the subatomic world that the vacuum is alive, that when you zoom down into the tiniest, smallest scales in the universe, particles, fields, energies are constantly popping in and out of existence, floating in and out of existence, being created, being destroyed in a flash of an eye. And this turmoil has an energy associated with it, that the vacuum of space-time itself has an energy. So if you take a box and you remove all particles, all radiation, everything, the box is empty, but that box has vacuum, and that vacuum of space-time has an energy all on its own. And then most recently, we have discovered that this vacuum of energy is causing the expansion of the universe to accelerate in an effect we call dark energy. We do not fully understand this process at all, but we do believe that it is connected to the vacuum of space-time itself. So charting this course, the article was so much fun to write, to chart the course from early experiments to even establish the existence of a vacuum, and then a reluctant acceptance of the idea, and then the realization that the vacuum of the universe is alive and has an energy and can influence the very largest scales in the entire cosmos.
What was your impetus or inspiration for writing about the emptiness of our universe now?
I actually am a expert. So the joke here is that experts are people who know more and more about less and less. I took that to the ultimate extreme. I, as a part of my research in cosmology, I study something called cosmic voids, which are the largest empty patches in the universe. These are the spaces between galaxies. These things stretch for hundreds of millions of light years, and they are almost entirely empty, especially in their deep interiors. My work involves studying them, mapping them, trying to use them to understand the evolution and history of the universe, and predict the fate of the universe. So I am dealing with nothing on a daily basis. And there's been a lot of recent advances in void research over the past year. And even though I didn't focus the article on the nature of voids themselves, this connection between the emptiness of the universe, where dark energy is, where the vacuum of space-time is, where the acceleration of the expansion of the universe is happening is all connected. And it just sounded like a fun thing to write about.
There was also a some recent research you highlighted, I think, from December about a survey kind of documenting.
Mhm.
Um, can you want to elaborate on that for us?
Right. So we are charting, or doing our best as cosmologists to chart the history of the universe and to make maps of all the positions of galaxies in the universe. We've made some progress. So far, we've mapped around a tenth of a percent of the volume of the cosmos. But hey, we just got started with this a few decades ago. So I believe we're doing a pretty great job. And the survey I mentioned is part of something called the Dark Energy Survey, which as the name suggests, is a survey of galaxies. It's a map of the locations of galaxies in the universe, trying to build a detailed map of the intricate structure of the universe at these incredibly large scales, and then tie that back to the properties of dark energy, this accelerated expansion. There's a lot about dark energy that we do not fully understand. We don't know how strong it is. We don't know if it's changing, if it's getting weaker or stronger with time. We don't know exactly when it turned on in the past and what drives it. And if you change any of these properties about dark energy, you change the overall structure of the universe itself. So by mapping the structure of the universe, we hope to understand dark energy better.
Gotcha. Um, what is the energy in the void? How much energy is in there? I think you said in the piece that it was infinite, but that's kind of hard to wrap your mind around. Is that just like a mathematical artifact of the theory, or do you think that it truly is infinite, like infinities are real?
Well, this is a great question because this is one of the major puzzles of modern cosmology and modern particle physics. So, if you just look at the bare math of quantum field theory and you ask, what is the energy of all these particles that are constantly fizzing in and out of existence? When you run the numbers, it comes up to infinity. And initially, when we first developed quantum field theory, these infinities did kill the theory because you couldn't make predictions. You couldn't do any math. You couldn't predict particle trajectories or paths. You couldn't get any physics done. But then people like Richard Feynman came along and figured out tricks to move the infinities around in the mathematics and push them to the side and still get uh, work done. We call this renormalization theory. We are able to use it to kind of sweep the infinities off to the side so that we can make predictions. And quantum field theory is an incredibly successful theory of fundamental interactions in our universe. The actual presence of an infinite amount of energy in the vacuum is not necessarily a problem because I like to imagine it as your height above your altitude above sea level. If say I'm sitting at this desk and I knock my lamp off the side of the desk and it falls 3 feet and it's going to smash on the floor. If my desk is at sea level, my lamp falls 3 feet and it smashes on the floor. If I move my desk to the top of Mount Everest and I'm 5,000 feet above sea level or even more, and I knock the lamp off the desk, when it hits the ground, it still fell 3 feet. And so all I need to care about in physics are those differences. It gets a little bit funky when you say, well, now take Mount Everest and make it infinitely tall. It turns out all that does is make the math difficult to work with. Um, you can still make calculations and still make predictions. Now, that's one side. That's particle physics straight up says an infinite amount of energy in the vacuum. But now we have these observations of the accelerating expansion of the universe. And we can measure that acceleration rate, and we can turn that around to say, how much energy is in the vacuum, and how much energy do you need to cause this accelerated expansion? And when you run those calculations, you do not get infinity. Otherwise, the universe would have blown up a very long time ago. You get a very, very small number. And it's very, very curious why particle theory predicts an infinite number, but then our direct observations tell us not infinity, not zero, but something very, very small. So we suspect something is up. Nature is trying to tell us something about the nature of the vacuum. We don't know what nature is trying to say to us. We're obviously getting something wrong with either our observations or our theory about the nature of the vacuum of space-time. But right now, we're still in the discovery phase. We just discovered dark energy about 2 decades ago. We're still trying to measure it. We're still trying to map it. We're still trying to wrap our heads around it. We honestly have no idea what's going on with the vacuum.
Yeah, I mean, sometimes counterintuitive things turn out to just be real? I mean, isn't it the case that when people realize that Einstein's theory of general relativity uh, resulted in singularities or black holes, they just thought, well, that can't actually be real. There must be something funky going on with the equations. But then we found, black holes out there. So, I mean, who knows?
Exactly. Yeah. Theories predict weird stuff in the universe all the time. Sometimes they're right and sometimes they're wrong. But now we have a clear-cut case when it comes to dark energy. We are observing the energy contents of the vacuum. We're just not exactly sure how to interpret that observation yet.
All right. So another question that I've always wondered about, but every time I hear an answer, I never seem like fully satisfied with it. But I'll pose it to you. What is our universe expanding into, if it is expanding as it seems to be?
That is a great question. The answer is that's not a great question. And it's a little bit tricky, so let me walk you through it. Yes, our universe is expanding. Our universe has no center and it has no edge. The Big Bang didn't happen in one location in space. The Big Bang happened everywhere. It happened everywhere in the cosmos simultaneously. The Big Bang was not a point in space, it was a point in time. It exists in all of our paths. When we say the universe is expanding, we mean that if you map a bunch of galaxies and measure the average distances between those galaxies, you'll get a number. And then you wait a little bit, a year, a billion years, whatever. And then you go to make the same measurement. Those distances, the average distances, are going to be larger. When we say we live in an expanding universe, we're saying that the distances between galaxies on average grows with time. And that's it. There's no center, there's no edge. From our perspective here in the Milky Way galaxy, it looks like the entire universe is expanding away from us. But if I go to literally any other galaxy in the entire cosmos, I get the same view. It looks like all the galaxies are expanding away from me. The universe doesn't expand into anything or from anywhere. The universe expands from itself and into itself. And I know that's very hard to visualize, but thankfully, we have these powerful tools like mathematics that allow us to grapple with techniques that even we can't imagine.
How is it that there's no edge? Because isn't there, wouldn't there have to be a frontier where the universe is expanding, where like the point at which it is pushing furthermost? I don't know if that makes any sense, but
Let
I
me
mean,
let me
if you
give you
just,
an analogy to navigate this. The answer is no. There does not have to be a frontier. There does not have to be an edge, and we can define this very well mathematically. But let me give you an analogy. I can ask you, what is the center of the Earth? And you'll say, yeah, it's the core where all the molten iron stuff is and all the mole people live. It's in the center of the Earth. Okay, you can point to that. But what if I were to ask you instead a slightly different question? What is the center of the surface of the Earth? If you constrain yourself just to the surface, just to latitude and longitude, give me the center of that. What is the latitude and longitude of the center of the surface of the Earth? There is no answer. There is no
incoherent
center.
question.
We have we have North Pole, we have South Pole, whatever, but those are arbitrary. You can put those wherever you want. And imagine our Earth was getting bigger and we were to measure the distance between New York and Paris, and then every year that distance is getting bigger and bigger and bigger. There's no center, there's no edge, and yet the distances between any 2 points still grows.
Yeah, yeah.
Yeah,
It's
it's
just
fun
the
stuff.
dimensions are, there's like an extra dimension to it because,
Yes.
right, we are
Yeah,
not
this is very
traveling on a
easy
surface.
to visualize in 2 dimensions. We live in a 3 dimensional universe. I can't imagine it. I can't think of it. I can think of the analogies in 2 dimensions, and I can trust the mathematics to take me into 3 dimensions.
Mhm. All right. You want to tell us any interesting tidbits or anecdotes or other ideas that you perhaps thought you might incorporate into this story, but decided not to? You go in a different direction. Any more about this
Yeah,
topic
yeah.
that you throw at us?
Yeah, when I initially started outlining this article, I thought I would bring in more of my research about the cosmic voids because when we look for dark energy, it's a property of the vacuum. So you have to go to the empty places. You're not going to find dark energy here in a planet or a solar system or even a galaxy because there's stuff. But dark energy lives in the voids. When you look at a great cosmic void that's 100 million light years across and almost completely empty of matter, it is full of dark energy. And so I thought I was going to incorporate that because, I love talking about my own research, but the path of the article just took a different direction, and I was totally happy with that.
So the universe expands more in the places where there's less matter. Is that what you're saying?
Exactly. The voids are currently growing, and the voids are in the present day act of ripping apart the large scale structure of galaxies in our universe.
Wow. That sounds really dramatic.
Yeah.
Um,
You can't make this stuff up.
yeah, truly. Um, so what are you working on right now? I imagine cosmic void stuff. Anything in particular you can share with
Absolutely.
us?
Unfortunately, I can't share a lot of it because it is embargoed with various collaborations and various groups. We just, some collaborators of mine released some papers about a month ago in December that discovered a bunch of very interesting void properties and linked this to mapping dark energy and constraining the properties of dark energy with future surveys. And then coming up, it's more the same. I just love studying them. They're like someone who's fascinated by dung beetles. I want to know all about them and know about their interesting properties and the best tools we can develop to uncover them.
I recently spoke to the astrophysicist Joseph Silk, who wrote a book about going back to the moon. And what he was really excited about is building massive telescopes in moon craters. And he was saying, describing how much better you'd be able to see the universe and things far away. What would you be able to do with a telescope on the moon that's hundreds of kilometers in diameter?
Yeah, Joe Silk is a fantastic scientist. I knew him very well when I spent my time in Paris. He's based at the Institute of Astrophysics in Paris. And yeah, there's been a lot of interest among astronomers of going to especially the far side of the moon to build radio telescopes, to build optical telescopes, to be free from light pollution, from radio interference. Um, in order to find the voids, you have to do big surveys. You have to go very, very broad so you can map out lots and lots of galaxies so you can find all the holes in the distribution. So, one approach you can take with giant telescopes is just to keep on mapping and go further, go wider to try to get as many voids as you can. The other thing you can do with giant telescopes is peer into the hearts of voids themselves. They are not 100% empty. There are very few faint dwarf galaxies. There's tendrils of gas. And understanding the interior properties of voids is something I've been interested in for a long time, and that requires very powerful telescopes.
Right on. All right. Before we go, do you want to tell our viewers how they can find you online, where they can follow more of your work and catch you on shows like this?
Absolutely. So my website, pmsutter.com, is the hub where you can find links to everything I do, including my podcast, Ask a Spaceman, my books, Your Place in the Universe, and How to Die in Space. You can also follow me on all social channels. I have the same name on all of them. It's at Paul Matt Sutter.
Excellent, Paul. It was illuminating to talk to you. Thanks so much.
Absolutely. Thank you so much for having me on.